Well, thank you very much to the organization for the opportunity they've given me to present my work. Thank you to Enoforum and Vason Iberica for coordinating it. This, well, to discover this new world, I mean, the title of my conference, Use of Hanseniaspora VINEAE, a new world to discover, has a bipolar function. These are the most abundant yeasts in grapes and in many fruits. In grapes, we know that more or less 50 to 80% of the native flora in the world that is present in the skin of the grape are apiculated species. Hansenia VINEAE is one particular group within this group. It is a subgroup in this group. And we are going to see how VINEAE is producing specific aromas and how it was discovered that they were having a potential application because they could ferment up to 10 to 11% of alcohol. And many of these piniculated yeasts that are normally existing in the skin of the grapes do not ferment that much alcohol. Remy is going to show some applications. The good news is that we've been making commercial wines for over 10 years with this yeast. And now we are starting a more massive application for this yeast. So it is giving out a type of fermentation that is very, very different to the usual fermentation that we see. And Tony Cordente's presentation came in very handy to present or to introduce this presentation, because he spoke about the honey flavors or aromas, these floral aromas, and the rosa element. And these are related to benzenoids, not only this compound, but many of these compounds that have this benzenic ring that derive from phenylalanine, tyrosine, and tryptophan. The specificity is that it produces an activity in beta-glucosidase at low pHs. Many glucosidase do not work at the wine pH, but this one does, and it increases the precursor aromas, so isoprenoids, for example, especially in red wines. And the other interesting thing is that it has a very high speed of autolysis respect to Saccharomyces cerevisiae. The autolysis in lees is giving more flavor in the mouth, and therefore the slower the Saccharomyces cerevisiae, the better. That's why we use this debourbage, and therefore it is much slower. I said faster, I meant slower. And it has a protease activity, which is a very interesting activity to avoid the excess bentonite, for example, or to stabilize white wines. And we are going to present a test on Sauvignon Blanc, in fact. The yeasts are just one of the aspects that are introduced by human technology for the last 30, 40 years. And the red arrows here indicate what normally happens in a certain and a specific terroir. In many places, irrigation is authorized. For example, external fertilization, that would be an external influence, and the application of commercial yeasts. The goal of this project was to differentiate ourselves from the rest, how to differentiate our wines in such a huge and global market as this. This is one of the goals that we enologists are looking for, and it was presented before me, or explained in the previous presentations. The most interesting thing is that to differentiate ourselves, what we do is to support ourselves in non-Saccharomyces, and this is why in the last 10, 15 years we've seen the fashion of resorting to mix cultures and the selection of non-Saccharomyces. It has a much wider selection of species and metabolic actions, and therefore this is the main goal, in fact, and therefore resorting to non-Saccharomyces or Saccharomyces, we try to, at the end of the 90s, we tried to change our strategy. We were thinking, okay, we can spontaneous ferment because spontaneous fermentation increases diversity, but they are going to be a risk for the winemaker and a headache. And we need to ensure that we do not run that risk. Some years it can go well, sometimes it does not go well. And the non-Saccharomyces do not always finish fermentation, but they are going to indeed leave a clear imprint, metabolic imprint in wines, and it will depend on whether the inoculation is co-inoculated or simultaneously inoculated, but it's going to enrich the wine, and this is one of the goals, in fact. In healthy grapes, we enriched with the species that are present in the skin of the grape. We use those, and there are some endophyte species in the grape. You can read the names on the slide. Normally, they are not good fermenters. They can contribute some enzymes or changes in the wine, but they are not good fermenters. And based on that, we were seeing that the apiculated, these types of species were 60–70% of the native flora that you can find here in Latin America, in Australia, in many countries. And this is what we were seeing a bit weird, because nobody was using apiculated yeasts. And our selection method was based on nose. We were carrying out some microfermentation since the 80s and 90s onwards with pure cultures. We smell, I like it, I don't like it, etc. And we made a collection that we have at the university with more than 800 different strains. And we found that there is no more than 5 to 10% of native strains with superior flavors in healthy grapes, which means that spontaneous fermentation runs considerable risks as well, because if 80% of your cultures are not going to give out good flavors or aromas, then that is a risk. And therefore, what did we do to try to discover and select those yeasts by flavor? That was the first stage, and then we are going to mention the fast cell lysis in the case of H. vinea, which is a typical characteristic of H. vinea and not other apiculated yeasts. You're going to see that this is an apiculated yeast that, as I said, is very abundant in grapes. And we are going to mention quickly something about extracellular enzymes compared to Saccharomyces, that is protease. We are going to refer ourselves to these 3 points, and we are going to see how we find the phenotype of flavor. And we did this at low levels of nitrogen, assimilable nitrogen. We designed a synthetic medium to standardize it in our harvest. because in the beginning we were working with musts, but musts do change year after year, and our goal was to work with yeasts that produce low levels of nitrogen, that do not produce sulfide. One of the products that they give out is sulfide, precisely. And if you see this, low nitrogen, less than 180, well, I have to say that when you see YAN here, Y-A-N, that means nitrogen assimilable by yeast. And most of the Enology in the 70s, we used to add ammonia, and then you enrich nitrogen. And what you did at that time was to lose aromas, sulfur aromas, the thiols, for example. They are lost in huge amounts when you add ammonia. And some yeasts can increase the number of esters, but some others can decrease them. And the benzenoids, the lower the nitrogen, the more benzenoids are produced, and they are fruity, attractive aromas. That's hence the challenge. I mean, we wanted to produce yeasts that give out rich aromas with less than 150 yen. We did that years ago with 100 milligrams of nitrogen in 2002 with simulated must in a proportion of 100 milligrams nitrogen per liter. A lot of commercial strains are fermented in this synthetic medium, and they give out unpleasant aromas, sulfide aromas that are not good at all, of course. And by using this method, we found only 5–10% of yeasts that were higher in aromas, and we tried to identify those yeasts that were higher in aromas, and we only identified 6 H. vinea and 3 Mechnicovia, some Pulcherrima, some other strains belonging to other species. And our attention was drawn to the fact that many of these yeasts were apiculated, and they did not have a good reputation. In fact, one of the explanations, we found it out when we sequenced the first apiculated yeast in 2012. You see here the corresponding publication, and the characteristic was that if you see, these are the fermentations of wines, and the Hansenia was producing less volatile compounds than Saccharomyces. Why is that? You can see the difference here in the photograph between an apiculated, because the daughter cells come out of one of the extremes, of one of the ends of the cell, and the cell on the right-hand side is a typical Saccharomyces cerevisiae that has many scars, let's say, because the daughter cells come out through different sides, which is shown in the scars. However, as I said, Hansenia VINEAE only gets their daughters out of the cell by the ends of the cell. And therefore, we worked in Uruguay, making wines up to 2014-15. This was a work carried out in Tarragona, doctoral thesis of one of our students with Macabeo, which is a neutral variety, a white variety, rather simple variety. And you can see here how the floral aromas were being enriched very intensely. Out of floral compounds, you will see in the next slides that they are compounds that are highly related to benzenoids. And therefore here in the red square, you can see Hanseniaspora VINEAE, which has a shorter genome than Saccharomyces, This is something that a lot of biologists know, that Saccharomyces cerevisiae duplicated or doubled its genome millions of years ago. However, the apiculated cells, did not do that. They are in the external group. They have a shorter and simpler genome. However, after these latest years, a lot of species were sequenced. Here you can see all the species sequenced of Hanseniaspora, and you can see that this group in red is the group where Hanseniaspora VINEAE is present, also Hanseniaspora osmophila and occidentalis, which is a species that we do not see very frequently in grapes. In other fruits, we do see it, but they are the fermentation group, the fermenters. They ferment double than the other ones that you find in the upper part of the slide, the ovarum, for example, the famous ovarum. And you will see why these apiculated were not having good prestige among these, because they are not accustomed to fermentation and they produced lactic acid. And therefore, if you make a wine with a pure culture of those, sometimes you got an unpleasant aroma. However, the fermentation group has a much, much higher fermentation capacity in the metabolic ways or pathways, and it can be seen that in the formation of acetaldehyde and ethanol, H. VINEAE has 8 copies. The hydrogenase alcohol, osmophila has 6 copies. It ferments with a bit more difficulty, and the other Hanseniasporas, belonging to the whole group of fruits, have less than 4 copies. And this generates a potential accumulation of acetic acid, or the lack of determination of fermentation, or excess acetaldehyde that is going to entail many problems with sulfites and accumulation of sulfites. This was done thanks to the importance of genomes and thanks to the sequencing, which allows us to explore more easily where we want to go to. Here you see that Hanseniaspora VINEAE and osmophila ferment at the same time as Saccharomyces cerevisiae, and Enoforum less than half of the Saccharomyces cerevisiae.
We all understood its metabolomes, the fruity aromas, dry fruits, some of them to sweets, and also the acetic analoids. Some of them are synthesized, some of them are augmented by the metaglycans. And the acetate, why does it produce so much intense aromas or aromas? That is a very particular feature of the Hanseniaspora VINEAE. We will see that in the next presentation. The other thing is the acetoin. It's like a buttery character, full-bodied character with the sensorial levels are lower. Here we can compare Uvarum, osmophila, and VINEAE. We thought that osmophila should behave in the same way as the VINEAE, but it didn't. We thought that VINEAE produced 100 times more of to phenylethyl acetate, over 100 times more than tyrosol acetate and tryptophol acetate, which are normally not very present, and they add some fresh flavor. This is a typical characteristic of VINEAE that can be seen in this right hand area. You see higher concentrations. And we wonder why. Then a simple thing was to measure the genes of VINEAE, and it has 5 copies of acetate transferryl acetase that are specific for higher alcohols, like the tyrosine and tyrosol and tryptophol, whereas Saccharomyces cerevisiae only had 1 active copy of acetyl transferase. That means that it had a wider range of genes. You see the comparison to the Osmophila that it does not have those genes and only one copy, so it does not acetyl these alcohols. So we were able to understand the whole process of that biology. Here you see 11 strains of Hanseniaspora VINEAE, all of them producing benzylic alcohol with almondry aroma. And here Saccharomyces that does not produce any benzylic alcohol. So we were able to understand the aromatic metabolites. And another thing that we discovered is that when you carried out industrial scale fermentations, inoculating after 3, 4, or 5 days Saccharomyces cerevisiae, when we only inoculated Saccharomyces cerevisiae, that is, as we say, is very selfish and wants to eat up everything and does not allow any other molecule to grow up, you see how it grew. And this was a later on inoculated strain, and the level of population was maintained similar, at similar levels at other strains living together. So the diversity that we lose, well, this is a scheme parting or starting in the vineyard, and you see how the diversity is reduced. So one of the challenges that we face is to recover this diversity. The strategy could be called, and we call it in a recent paper with colleagues from Australia, that they are kind of more friendly, less selfish, the VINEAE, than as compared to the Saccharomyces cerevisiae. So this was our conclusions about flavor. I think I am sticking to my time, I think. Now let's talk about the cell lysis. Let's just see a few slides. You see how Hanseniaspora uvarum produces quite a good amount of flavory aromas and fruity aromas, but with a certain amount of defects. And all the apiculated must die. We thought they must die very fast. This what you see here is the cell viability and the membrane integrity. After 15 days of fermentation of the H. VINEAE, these integrity is lost, whereas in uvarum and Saccharomyces, they do not allow for that fast lysis. Why so? From the technological point of view, it's interesting because we really achieve the full body character that we want in a 9 months aging sparkling rosé. And this is one of the interesting outcomes. And the other thing that we saw is that they did not behave exactly the same. So, well, we will be publishing these outcomes in the short term, but we did not find any other Hanseniaspora that died so fastly. We understood that they die as soon as sugars disappear. As soon as they disappear, she starts dying. It starts like a suicide process, and this allows for a more accelerated death of the cells. We are learning that ammonia addition also accelerates the death of VINEAE. So if you think of using VINEAE, but then you add ammonia, because it won't, she's not going to use it because she would work much better on environments with low nitrogen levels. If we want to kill it more fastly, we should add ammonium. If we do not want it to die so fast, we should not add any ammonium. It's just things that we are learning as we work on these species that has nothing to do with the Saccharomyces. Now about protease. to reduce the use of bentonite, you know that the minimum intervention means the less we manipulate the wine, less aromas we lose. That is rather easy to understand. There is no other way to act. That's why the new trend of non-filtered wine started, with less and less intervention of external additions. You would be losing aromas in the Sauvignon Blanc, for instance. So we carried out some trials in Sauvignon Blanc, and we saw how the H. VINEAE had a very active protease, such as like this one. The green one is Saccharomyces, that's the control. It's a strain of Chardonnay. In this other column, it's 5 times less proteins. In Sauvignon Blanc with H. VINEAE, so that means we will find 5 times less bentonite, so we would need to intervene much less. Here you can see a trial with 35 trains that we are still carrying on, but I would like to summarize and leave my colleague Remy Schneider to present its more applicated part. In the end, VINEAE needs open air. That's good for stabilizing tannins and color. It also likes working at 18 degrees and not at all 25 degrees. She loves working on between 15 and 22 degrees max. It is good for young red wines, but also for warm climate wines, because many enologists think that in warm climate environments we need to cool down, but no, they need just low nitrogen also. We don't need to add nitrogen after the Saccharomyces cerevisiae, as Remy will show in a bit. And then we might use some vitamins or any other component. This is more or less the characteristic features. The first that we produced and more easy to assess were white wines and Tannat, as a typical Uruguayan variety, because Tannat is very structured, is very colorful, but not too much aroma, very weak, fruity aroma. And then we were able to enhance the potential. And Chardonnay is also easy to avoid batonnage in the cascade. There's no need for any other thing. And the other interesting thing, I think it's what you are more interested in, is where we have neutral grapes, where we have tons and tons of grapes in the world, Macabeo, Trebbiano, or Uni Blanc in France, Albillo, that's another variety from the Duero basin. These are like neutral grapes, and they are benefited from this addition. Also Petit Manseng, barrel fermented, this comes from the Basque country, related to Tannat. And this is our main message, that there is an opportunity to build a new yeast range with Hanseniaspora VINEAE that allows terroir to be expressed. We have we had 35 genetically differentiated strains, which is rather rare because you don't normally find this in the fruit, because we were able to understand how to identify it or how to locate it. And this is easily melded with the terroir. So the conclusion, the flavor, 20 times more than the Saccharomyces with of aromatic alcohol, acetates and benzenoids, and higher alcohols derived from aromatic compounds. A fast lysis, this is particularly interesting There are cuvées being made, sparkling cuvées, because it really gives us a lot of body. And then active enzymes in wine conditions, in pH wine conditions, because many times we have yeast with these active enzymes, but when you have pH like 3.2, 3.3, they are not very functional.